Hi everyone, welcome back to my YouTube channel. I am Reeti and I am back with another lecture in the DBMS series. So in the last couple of lectures we discussed about isolation level and types of isolation level. In this particular video we would be discussing on schedules. So without any further ado, let's get started. Now what is a schedule? So schedule refers to the sequence in which a set of concurrent or you can say multiple transactions are executed. You can also say it as a sequence in which the operations such as read, write, commit and abort of multiple transactions are getting executed. So consider if there are two transactions T1 and T2. As part of D1 we are doing some read operation. As part of T2 we are doing some write operation. So the time order sequence in which these operations of multiple transactions are getting executed, that is what a schedule is. Now it is really helpful to ensure data consistency and integrity. Since it tells us that what is the sequence in which the operations are getting executed, it is very helpful in maintaining the data consistency and integrity of database. Consider if there are some transaction T1, T2 till Tn, then the possible number of schedule is n factorial. So if there are two transactions, the possible number of schedule is 2 factorial. Now here if you can see there is a schedule SC1 where we have two transactions T1 and T2. We have mentioned all the operations which are happening in these two transactions including the read as well as write operation. Now here you can see that we are getting a time order sequence, like first T1 started its read operation, then there was a context switch, then T2 started its execution, then again there was a context switch, then T1 committed the data, then again there was a context switch and T2 committed the data. So we can know the time order sequence or the sequence in which the multiple operations of different transactions are getting executed. Now here you can see that in the schedule we can see the commits. So if commits are present in the schedule, we call it as a complete schedule. If commit statement is not present in the schedule, that is changes are not saved into the database, we call it as incomplete schedule. So let's see in more depth. So incomplete schedule is a schedule where not all transactions have reached their final state of either commit or abort. So final state in any transaction is either commit or you can say rollback. So if the transaction succeed, we commit all the changes into the database. If transaction does not succeed or face any network failure or system failure, we roll back all the changes. So whenever some of the transaction in a schedule does not reach its final state, we'll call it as incomplete schedule, and when they reach, we call it as complete schedule. So here you can see that there are two transactions T1 and T2. T1 performed some read as well as write operation, then there was a context switch, then T2 performed some read as well as write operation, then there was a commit which was done for T2, but there was no commit which was performed for T1. So we can say that this is an incomplete schedule because T1 hasn't reached to its final state and is still in progress. So whenever any part of transaction which is a part of schedule which hasn't reached to its final state, we call it as incomplete schedule. Now coming to complete schedule, so a complete schedule is one where all transactions in the schedule have either committed or aborted, basically have reached their final state. So here if you see there are two transactions T1 and T2. T1 started its execution and reached its final state, so T1 is already in its final state. Coming to T2, T2 started its execution and reached its final state. So here both of the transactions T1 and T2 are in final state, so we can call it as a complete schedule. So basically if the transaction in a schedule has reached its final state, we call it as complete schedule. If they haven't reached its final state, we call it as incomplete schedule. Now coming to the types of schedule. So the first one is serial schedule, the second one is concurrent or non-serial schedule, third is conflict serializable, fourth is view serializable, fifth is recoverable, sixth is irrecoverable, seventh is cascadeless, eighth is cascading, and ninth is strict schedule. So let's learn about each and every schedule in depth. So coming to the serial schedule. So a serial schedule is one where transactions are executed one after another. We can say it like if there are two transactions T1 and T2, then T1 should commit to completion before T2 starts. So according to serial schedule, if there are two transactions T1 and T2, so T2 should only start when all the operations of T1 are committed or either saved in database, or we can also say have reached their final state. So once they have reached their final state, only then T2 can start, else T2 can't start. So if you see the schedule here, there are two transactions T1 and T2. T1 started its execution, read A, write A, and then there is a commit. So T1 has reached to its final state. Now now only T2 can start. Before this, T2 can't start. So there is a serial execution. First T1 will complete all its operation, then T2 will start its operation and complete it. Then T2 started, and here T2 also completed. So you can say that T2 starts only after T1 is completed, committed, or reached its final state. Now here you can see that there is a serial execution which happens, like first transaction T1 will be completing, then only T2 will be starting. That is why it is known as serial schedule, because it has serial execution of transactions. So let's see the advantages and challenges which is faced in the serial schedule. So coming to the first advantages, it follows the ACID properties, that is transactions are isolated from each other. So in the serial schedule, what happens is, if there are two transactions T1 and T2, T1 needs to perform all its execution, only then T2 can start. So we can say that these particular transactions are isolated of each other. Any operation of T2 can't go ahead and hamper any operation which is getting performed in T1. So there is a level of isolation which is maintained between T1 and T2, because T1's all execution are done, only then T2 starts. Now the second point is, it maintains consistency. So consistency is obviously maintained here because T1 is committing all the changes into the database once it's succeeding. So even if we start T2 and even if we perform some operation on the same data item, all the data has been updated into the database. So there is no data inconsistency which would happen, because there won't be any read write, write read conflicts which would be occurring. So we won't be going ahead and updating any invalid data in our database. T1 has committed all the changes, T1 has successfully updated it in the database, and then only we are performing operations of T2. So let's see the challenges. First challenge is, since there is a poor throughput, that is number of transactions completed per unit time, and the memory utilization is also poor, that is why it is not suggested, as it can be inefficient. So consider in the serial schedule, if there are two transactions T1 and T2, T2 needs to wait for T1 to get completed, but consider T1 take 5 minutes to get completed. So T2 can only start after 5 minutes. So if you see the throughput, that is number of transactions completed per unit time, is very less. That is why there is a poor throughput. And memory utilization is also poor, because if T1 is executing all its operation, T2 is sitting idle, and CPU core is only able to succeed all the T1 operations, not the T2 one. So T2 is sitting idle, and CPU cores are also not getting utilized to its max. So we can say the memory utilization is also poor. The second is, since wait time is high, less number of transactions are completed. Now T2 needs to wait for T1 to complete, and T1 is taking 5 minutes. So the wait time is very high. In 5 minutes, in a real life scenario, there should be 1,000 or more than 1,000 transactions which should be done. But here, in that particular time, only one transaction is getting completed. So because of all these reasons, it is suggested not to use the serial schedule, even if it has a higher consistency, but the throughput is very low, the number of transactions getting completed per unit time is low, memory utilization is low, or you can also say the wait time is very high. So because of all those things, serial schedule is not suggested. Now coming to the second schedule, that is a non-serial, or you can say concurrent schedule. Now from the name it's clear, non-serial, so there is no serial execution. So a non-serial schedule is one where multiple transactions can execute simultaneously. Operations of multiple transactions are alternate or interleaved. So what is this alternate or interleaved? So here if you can see, there are three transactions, T1, T2 and T3. Here T1 started its execution, then there was a context switch. T2 started its execution, then again there was a context switch, and then T3 started its execution. So all these transactions are starting their execution simultaneously. So these are interleaved, or you can say alternate execution. We can say it like, if there are two transactions T1 and T2, T2 doesn't need to wait for T1 to commit. It can start at any point. So if you see from example, T2 or either T3 can start their execution. They don't need to wait for T1 to get completed. That is what a concurrent schedule is. So here T2 didn't waited for T1 to commit. Now here you can see that at later point T1 is committing its changes, but T2 and T3 have started their execution. So the wait time is very low. Now coming to the advantages and challenges, first is better resource utilization, because at the same CPU core T1 is also starting their execution, T2 is also starting, T3 is also starting. So resource is getting utilized at its max. Second is wait time is not involved, because T2 doesn't need to wait for T1 to get completed. One transaction doesn't need to wait for running one to finish. So the next is throughput is very high, that is the number of transactions getting completed per unit time, because T1, T2, T3 all are starting at some instant of time and they are not waiting for other one to complete. So it is starting at this particular point, it is starting at this time, it is starting at this time. So at some time t double dash, we will be able to get all these transactions getting completed. So the number of transactions getting completed per unit time would be more. Now coming to the challenges. So first is consistency issue may arise because of non-serial execution. It requires robust concurrency control mechanism to ensure data consistency and integrity. Now in non-serial execution, what happens if there are three transactions T1, T2 and T3? As part of T1 we are reading some data item, as part of T2 we are writing some data item, as part of T3 we are reading some data item. So we have read the data item A, then we have written or updated some value of data item A, then again we have read the value of A. But consider at some point this T2 fails. So this particular transaction T3 has read the value which was there in T2 or which was updated from T2, right? But this particular transaction failed, so there won't be any update happen. But as of now, the T3 has read the value which was updated here. So this particular value becomes invalid and there is data inconsistency which happens. So that is why there are some concurrency control mechanism which make sure that these particular things doesn't happen, and serializability concept is also there for this. So we can use serializability and concurrency control mechanism to ensure consistency so that none of the invalid data is updated or there is no inconsistent data which is present in our database. So coming to the third schedule, that is conflict serializable schedule. So a schedule is conflict serializable if it can be transformed into a serial schedule by swapping adjacent non-conflicting operation. Now what are these conflicting and non-conflicting operation? So consider if there are two transactions T1 and T2, we can perform some operations on them. Consider there is a read operation on T1, read operation on T2. Read operation on T1, write operation on T2, write operation on T1, read on T2, and write in T1 and write in T2. So here if you see, if we perform read operation on T1 and T2 both, so they are reading the same data item although, but they are reading the same value, right? They are not updating anything, they are reading the same value, so there is no issues here. But coming to here, if any transaction we are reading some value and at part of next transaction we are updating that particular value, so there will be a read write conflict. Coming to this, so if at part of one transaction we are writing some value or updating some value and as part of another transaction we are reading that particular value, so there will be a conflict. Coming to the same write, if we are writing some value as part of one transaction and then again writing some value of part of another transaction, so there will be a conflict because there could be a possibility that we are reading some value and here we are updating some value, but at some particular point this particular transaction fails. So if we are reading the value again, we will be reading inconsistent value. So these all operation can cause inconsistency. You can say that whenever there is a write operation involved, it can cause inconsistency. So we call these pairs as conflicting pairs. Because of these, there could be some conflicts which can arise or there could be inconsistency in data which can arise. And this pair is non-conflicting because even if we are performing read operations as part of multiple transactions, there is no issues. So here you can see the conflict pair is read write, write read, write write when performed on the same data item. But there could be a possibility that as part of T1 I am reading the value of A, but as part of T2 I am writing the value of B. So here the data items are different. So these are also a non-conflicting operation. So if we go to the non-conflicting pair, read read when performed on the same data item, read read when performed on the different data item, write write when performed on the different data item. Since we are performing on different data items, so there would be no consistency issue because we are not going ahead and updating the value of B, we are going ahead and updating the value of A, and we are reading the value of B, so there won't be any issues. So let's come back to the conflict serializable schedule. So as part of conflict serializable schedule, what we do is we take the concurrent schedule, we change its execution from non-serial to serial so that the consistency issue which was coming in non-serial execution, or you can say in the concurrent schedule, is encountered or taken care. So what we do here is we find a conflict equivalent. How we can find a conflict equivalent? By swapping the adjacent non-conflict pairs. And in that conflict equivalent, we see that if by swapping we are able to achieve a schedule where there is no conflicts. So coming to this schedule, if we see the non-conflicting adjacent pair, so T1 has read of A, T2 has read of A. So this is a non-conflicting pair because we are performing only read operation on the same data item. Coming to T2 and T1 again, read of A, write of A. This is conflicting. Coming to here, write of A, again conflicting, and then write of B. So here we can see that there is only one non-conflicting pair. So what we have to do is we have to swap these non-conflicting pairs, and then we can get the conflict equivalent, and then we can see that if that conflict equivalent has any conflicts or not. For now, we won't be looking much more depth into this particular schedule because we have a dedicated lecture on conflict serializable schedule. So here you can see that RA of T1 and RA of T2 is non-conflicting, RA of T1 and WA of T2 is conflicting, having read-write conflict, and WA of T1 and WA of T2 is conflicting because they have write-write conflict. So the fourth schedule is view serializable schedule. Now it is also part of serializability. So serializability is a method which is used so that we can encounter the inconsistency issue which was coming in the concurrent schedule. As part of serializability, we do a conflict serializability and a view serializability. So we would be learning about all these in next set of lectures. So view serializability ensures that the database state seen by the transaction in a concurrent schedule can be replicated by some serial execution of those transactions. So in view serializable schedule, or you can say view serializability, we are making sure that if there is a concurrent schedule, they have a serial execution so that the consistency issue is encountered. Now, whenever we find a cycle in our conflict graph, we don't know if our schedule is serializable or not, so we use the view serializability here. So serializability is used to encounter the inconsistency issue which was coming in our concurrent schedule. Now, as part of serializability, there is conflict and view serializability. In conflict serializability, we draw a conflict graph. Now, if this particular graph has any cycle, we go to the view serializability to check if this schedule is a serializable schedule or not. If there is no cycle, we can say that this is a serializable schedule. If there is a cycle, we go to the view serializability and check for some conditions for a view equivalent. If all these conditions are met, we say that this particular schedule is a serializable schedule. If not, we say that this particular schedule is not serializable. Now, all these things may be sounding confusing to you, but don't worry, we would be talking about each and everything in depth in next set of lectures. For now, you can only think that view serializable schedule is a schedule which is view serializable. So a schedule is view serializable if its view equivalent is equal to a serial schedule execution. So whenever a schedule is view serializable, its view equivalent is equal to a serial schedule or serial execution. So whenever there is a serial execution of a view equivalent which we have found out for a schedule, we call it as a view serializable schedule. So coming to the next schedule, that is recoverable schedule. So a recoverable schedule ensures that if transaction reads data from another transaction, it should not commit until the transaction from which it read has committed. So consider if there are two transactions T1 and T2, and T2 is reading some data which is updated by T1. So T2 shouldn't commit until the time T1 commits. So T2 should always wait for T1 to commit, only then T2 should commit. If it commits before, and what if at some point this transaction fails, this particular operation will read some invalid data, because as T1 failed, there was a rollback and this particular operation is nullified now. So this data is invalid. So we have to wait for the transaction from which we are reading the data to be committed so that we commit the correct, or you can say the consistent data. So this helps in maintaining the integrity of database in case a transaction fails. So if at any point T1 fails, we will be able to recover T2 because T2 hasn't committed all the changes into the database. It's present only in the transaction logs. Now coming to the sixth, that is irrecoverable schedule. An irrecoverable schedule allows a transaction to commit even if it has read a data from another uncommitted transaction. So if the transaction is uncommitted, it allows another transaction to commit the data. This can lead to inconsistency and make it impossible to recover from certain failures. So what if transaction T1 fails at some point and we have committed the data based on what we have read from the updated value of T1, which is not updated into the database because the transaction has failed. So this will have an invalid data, and that particular invalid data would be committed or changed into the database. So it will cause inconsistency in the database because we are updating some invalid value or the value which is not consistent into our database. So the next schedule is cascading schedule. This schedule happens when the failure or abort of one of the transaction causes a series of other transaction to also abort. So consider if there are 3 transactions T1, T2 and T3. T1 has started its execution, T2 also started and T3 also started. At some point T1 failed. So here you can see that there was a write of A which was present in T1 and T2 read the same data which was updated as part of T1 but T1 failed. So this also needs to abort and this also needs to abort because we won't be updating any inconsistent value or we won't be reading any inconsistent value which is not updated in our database. So there are multiple aborts which are happening. So here you can see T1 writes to A, so T1 writes a data item to A, T2 reads it, so T2 reads the uncommitted value of A which is written by T1. Now if T1 fails and aborts, T2 must also abort because it has read an uncommitted value which is from T1 and this particular value is also read by T3, so T3 also must abort. Now there are some issues. First is the performance degradation because multiple transaction needs to be rolled back. So there were some transaction which started but because of one transaction failure there are multiple rollbacks which is happening. So there is a performance issue. Second, improper CPU resource utilization because we use the CPU resources to perform these 3 transactions but because of the failure of one transaction all the transactions have to fail because they have read some uncommitted changes of that particular transaction. Now coming to the next schedule, that is Cascadeless schedule. So it ensures transaction only read committed data such that the abort of one transaction does not lead to the abort of other transaction that have already read its uncommitted changes. So it makes sure that if any transaction is reading any value, it should always read a committed value. It shouldn't read a value which is not committed. When a transaction has already committed all its changes to the database and if we are reading the committed changes, there is no issues which will occur here because these are all the changes which are saved into our database and there is no chance of failure which occurs after commit because this is the final state. So this particular read operation won't have any inconsistent data. So T1 writes to A, T1 has written some value to A and T2 reads from A. So T2 reads the committed value of A because it has been saved into the database, ensuring that there is no write read problem which is happening. So in the cascading schedule there was a write read problem which was happening but here it is not happening and T2 does not read any uncommitted data because this data is committed. So there is no cascading aborts in this particular schedule. But here it says that one should only read committed data. But what about the write operation? So they haven't told anything about the write operation. They have only told about the read operation, that one should always read the committed data. But what if there is a write problem which can come, right? So there are some issues. First is the write problem is encountered because it has only told that it can read committed data but not anything related to write operation. Second is performance overhead is there because again this needs to be committed, so this particular transaction can only read after it is committed, so it needs to wait for this to get committed. Coming to the last schedule, that is strict schedule. So it ensures that transaction is not allowed to read as well as write a data item that another transaction has written until the first transaction has either committed or aborted. So it makes sure that there is no read or write operation performed until that particular transaction from where we are reading or writing the data has been committed or aborted, basically has reached its final state. So it prevents the cascading aborts. So what will happen in T1 and T2? So T1 needs to complete all its operation, only then there could be any read as well as write operation which would be performed. So the write issue which was coming there or write conflict which was coming there is resolved now because it can only write a data or it can only read a data once the transaction is committed. So T2 cannot read or write the value of A until T1 has committed. This ensures that T2 only sees the committed value of A. So this is how strict schedule prevents the cascading aborts and make the consistency at its peak. So this was all about schedule and types of schedule in this particular video. I hope you like this video. So if you like this video, please hit the like button. If you're someone who is new to my channel, can go ahead and watch out the tech content first, and if you find it useful, can go ahead and subscribe. Also, if you have not followed me on my social media handles, you can go ahead and follow. The links are in the description. Till then, take care, keep learning, keep growing, keep smiling. Bye all.